Hi, I'm Herbert Gross, and welcome once again to Gateways to Algebra, lecture number 6, where today we're going to introduce a new topic called exponents. Now, you may have noticed that I did one sort of simple thing several classes ago, and it got us off into a series called Signed Numbers. Just one little change in wording. Remember what we did? We had the command say subtract 15. Now, let's suppose that my computer understood English, but it only understood a very limited vocabulary. It would understand subtract. This is called the constant, by the way, 15, because no matter what number I start with, to subtract 15 is not going to depend on what number I began with. The answer might depend on what I began with, but subtract 15 is 15 no matter what I started with. So that's called the constant. So our computer can add a constant, subtract a constant, multiply by a constant, and divide by a constant. But it's not used to seeing any word between the arithmetic operation and the number. So what happened was, when we said subtract from 15, that one word caused the computer to say, I don't understand what's happening here. See, the computer was programmed that after the word subtract, it had to hear a constant. And when that constant didn't appear, the computer wasn't able to handle this. Now, what's going to happen next is I'm going to give the computer a new command early in this lesson where I'm going to tell it to do, I'm not going to say subtract from, I'm not going to put any extra words in, but I am going to change the arithmetical operation in the sense that we will not operate with a constant, and watch what happens. But the thing I want you to notice is that just changing one word, like the word from, caused us to develop a whole new theory. You see, in a logical subject, such as mathematics, but any logical subject, what's amazing is that when you change or add just one rule or one definition, you don't just get one new piece of information, you get book after book of new ideas to think about. So let's review lightly by doing something we could have done before. Let's do this. Let's take the program where we pick a number, multiply by 2, add 1, multiply by 3, and write the answer. You see what's happening? We're multiplying by a constant, we're adding a constant, we're multiplying by a constant. You see what I mean by a constant? No matter what number I pick, multiply by 2 doesn't depend on what number I picked. The answer does, but the operation doesn't. When I say add 1, that happens regardless of what answer is up here. In other words, to do any one of these steps, I only have to look at the answer that came before. So for example, if I pick a number, let's suppose I just pick 6. I multiply by 2, the answer is 12. I add 1, answer is 13. I multiply by 3, the answer is 39. Okay, nothing new here. And now let's reverse the process. If the answer was 39, to undo multiplying by 3, I divide by 3. To undo adding 1, I subtract 1. To undo multiplying by 2, I divide by 2. And now notice what I've done. Notice if I now read this list from top to bottom, have exactly the same thing that I had over here. So far, so good. Now, watch what I'm going to do instead. This time, I'm again going to start with x. But now, I'm not going to multiply by a constant. I'm going to multiply by the input, okay? In other words, I start with x, I multiply by x itself, I add 1. Now whatever answer I get, I multiply by x again. Now notice what's happening over here. You see, when this says multiply by x, it's not enough to know what the answer was on the add 1 line. I have to go all the way back and find out what x is. So let's see what happens over here. Suppose I knew that the answer was supposed to be 17. What have we been doing up until now? We said, when was the answer 17? The answer was 17 after we multiplied by x. Therefore, to find out what answer we had on this line, what we really should do is take the 17 and do what? Divide by x. What's the problem with this command? What's the problem with dividing by x? The answer is, if we knew what x was, we wouldn't be doing this problem. We're told that the answer is 17. We're being asked to find x. how can I divide by x if I don't know what that is? You see, if this step over here, instead of multiplying by x, had been multiplied by 3, then could I have taken the 17 and divided by 3? See, as long as there's a constant here, I don't have to know what's happening. You see the problem? When I start at the top, I know what the input is, so any command that says do something with the input is fine. I just go back to the beginning and use the input. The problem is, when I'm given the answer and I'm giving a command that involves the input, I have to go all the way down to the beginning, and I don't know what that is. But by the way, even though I can't do that, I want to pause here for a few minutes to show you something else. Don't ever believe you can't do a problem just because a particular method doesn't work. There are other methods, and don't ever give up on trial and error. For example, I could say, I don't know what works, but let me just take a wild guess. I'll try 2. Input is 2. It says what? Multiply by x, multiply by the input. 2 times 2 is 4. Add 1, 4 plus 1 is 5. Multiply by x, I go all the way to the beginning. X was 2, 5 times 2 is 10, so the answer is 2. Did I guess right? No, because if I guessed right, the answer would be 17. Well, my guess was too small. I'll just try something bigger. I'll try 3 this time. What do I do next? I multiply by the input. Do you see the difference already? You see, when the input was 2, I multiplied by 2. When the input is 3, I multiplied by 3. See, what I multiply by is a variable. It depends on what I picked. It is no longer a constant. But watch how easy the arithmetic still is. Start with 3, multiply by itself is 9, add 1 is 10, multiply by the input was 3, 10 times 3 is 30. This time the answer is 30. Oops, I guessed wrong again, but this time I guessed too big. Well, if 2 is too small to give me the right answer, and 3 is too big, something between 2 and 3 should give me the right answer. Well, 17 is closer to 10 than it is to 30, so I'll try a guess that's between 2 and 3, but closer to 2. Well, I'll try 2.4. And by the way, notice how the theory doesn't change now, but how the calculator becomes a big help. When I say start with 2 and multiply by itself, that's not a hard thing to do. But if I say start with 2.4 and multiply it by itself, that would be a little bit more tedious, won't it? But with the calculator, I get 5.76. Add 1, it's 6.76. Multiply by the input, I take the 6.76, multiply by the 2.4. Now I get what? 16.224. Still the wrong answer. Still a little bit too small. But isn't this starting to become closer to the right answer? In other words, if the input was 2.4, I would almost get 17 as the output. And by the way, watch how I can keep going this way. If 2.4 gave me something that was too small, let me try 2.5. If 2.5 is still too small, I'll try something bigger. If it's too big, I know my answer is between 2.4 and 2.5. And I'm going to leave the details to you, but watch what happens. The recipe doesn't change. All that changes is, as the input changes, then these commands also change because they use the input. I start with 2.5, multiply by 2.5 gives me 6.25, add 1 gives me 7.25, multiply by 2.5 gives me 18.125. 17 is between 16.2 and 18.1, so I know 2.4 is too big, too small, 2.5 is too big. So I'll split the difference. I'll try 2.45. I multiply 2.45 by itself. I get 6.0025. Add 1 gives me 7.0025. Multiply by 2.45, the input, gives me 17.156125. Again, this one is too small. This one is too big. So I know the right answer is someplace in between. Let's suppose I just try 2.44 for the sake of argument. Okay? 2.44 times 2.44 is 5.9536. Add 1, multiply by 2.44. I wind up with 16.966784. I'll try that's again what? Too small? I'll try something a little bit bigger. 2.442. Go through the same steps. Multiply 2.442 by itself. Gives you 5.963364. Add 1. 6.963364. Multiply by 2.442. Gives you 17.00453489. Look at this. to 2 decimal place accuracy, you now have the right answer. Do you see what a terrific thing the calculator is? Look at how fast I did those computations. Could I keep going and getting more and more accuracy? And after all, if I had a computer, all that would do is these same steps, only so fast that it would just keep on whirling around and grinding out the answer to as many decimal places as I want, almost faster than I could keep up with it. You see, the real question we have to deal with, and this will come up over and over again in our course, is how close is close? How close do you have to go before it's close enough? For example, suppose you're buying oranges and they're 3 for $1. That means they should be 33 1/3 cents each. Now, if you round off 33 1/3 cents to the nearest cent, they should only charge you 33 cents. But if they only charged you 33 cents, you wouldn't buy 3 for $1. You'd buy 3 separate ones for 99 cents. So they charge you 34 cents. Okay? Now, the problem is, usually, if you pay 34 cents instead of 33 cents, will that bankrupt you? The answer is no. You're only off by 1 cent. But what if you were buying a million like this? You see, if you lost 1 cent 1 million times, that's already $10,000. That's a pretty big amount. In other words, how much you can afford to round off by depends on the problem. Therefore, what you want is a recipe that will give you more and more accuracy as you need it. But let's see what was happening over here by virtue of multiplying by the variable. See, suppose I start with x. When I multiply by x, I get x times x, which you may remember from arithmetic is called x squared. When you multiply a number by itself, that's called squaring a number. You see, that causes a problem. See, every time we multiply by the input, what we're doing is we're increasing this exponent, as it's called, by 1. See, start with x, multiply by x, x times x is x squared. Multiply by x again, you have what? 3 factors of x. The problem is when you have terms involving x to the third, x to the second, and x, and you want to combine them. You can't combine these because each of these adjectives is modifying a different noun. See, if you started with x and added x and added x, it doesn't matter. If you had 3 x's and 2 x's and 4 more x's, since the 3, the 2, and the 4 all modify x, nothing new is happening. See, that we can add what? The 3, the 2, and the 4 to get 9 because they're all modifying the same noun. You see, and by the way, this is kind of sloppy. If I say to you, how much is 3 fours, what answer will you usually give me? How much is 3 fours? Well, a kid in the first grade might say it's 444. See, there's 3 fours. Usually we say what? 12. We usually hear it as 4 plus 4 plus 4. The word sum, S-U-M, isn't in here. We don't say how much is the sum of 3 fours. We say how much is 3 fours. But could it also mean the product of 3 fours? See, this is a very ambiguous remark. How much is 3 fours? So what we're going to do now is, when you mean to multiply, we're going to introduce this new notation. The 4 over here will be called the base. The little number you write above and to the right of the 4 is called the exponent. And this will be read 4 to the 3rd power, sometimes called 4 cubed, which we'll explain later on. Up to the 3rd power, we usually say square, cube, then we say 4th power. It doesn't matter. But 4 to the 3rd power means you're going to multiply 3 fours. See, the bottom number tells you what number is going to be multiplied by itself, and the top number, the exponent, tells you how many times that number appears as a factor. So 4 to the 3rd power means 4 times 4 times 4, and that's 64. Okay? By the way, notice the difference of interchanging the exponent with the base. If I interchange these, I get what? 3 to the 4th power? The base tells you what number is being multiplied over and over again, and the exponent tells you how many times that factor appears. So this says what? You're multiplying 4 factors of 3. 3 times 3 times 3 times 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. See, 4 to the 3rd power is 64, 3 to the 4th power is 81. Notice how unlike that is from multiplication. See, 3 times 4 means 3 plus 3 plus 3 plus 3 that's 12. 4 times 3 means 4 plus 4 plus 4, which is 12. Notice, by the way, that even though people tend to say 3 times 4 equals 4 times 3, because all you did was change the order, which is really a big deal, changing the order, notice that when you look at this line here doesn't look at all like this one over here. It's not so obvious that when you add up 4 3s, you're going to get the same answer as if you added up 3 4s. However, that's not hard to see with tally marks. See this arrangement? I have what? 4 in a row. See? 4 in each row. And I have what? 1, 2, 3 rows. So I have 4 3 times. On the other hand, I have what? 3 in each column, and I have 1, 2, 3, 4 columns. So all we're saying is what? 3 rows of 4 is the same number of tally marks as 4 columns of 3. So anyway, we're now talking about raising numbers to powers, and let me show you how powerful that is. Let me show you the difference between adding 2 and multiplying by 2. Suppose you bought an item in 1900 that cost $1. And let's say that the cost of that item doubled every 10 years. So in 1910 it would cost $2. 10 years later, it's the $2 that's the new price. That doubles to 4. 10 years later, the 4 doubles to 8. 10 years later, it doubles to 16. 10 years later, the price doubles to 32. You see, it's always doubling over the new price. In 1960, it would be 64. 1970, it would be 128. 1980, it would be 256. 1990, it would be 512. By the way, if a person who was a real old-timer said, I don't know why you guys can't live today, we used to get by on $4 a week when I was a kid, remember, that $4 could have been 2,000. And there's a lot we can talk about that, but in the interest of just introducing the exponents, I thought I would just mention a few things like this. If you wanted to leave a lot of money for somebody, in fact, Benjamin Franklin did this in the 18th century to found Franklin Institute, where he put away a certain amount of money at a certain amount of interest and said, you can't touch this money for 200 years. Look what happens over here. For every dollar you invest, if you could double that value in 10 years, okay? If you could do that, what that says in 100 years, every dollar that you invested would now be worth over $1,000. If you would put away $1,000 here, you'd have over $1 million in the year 2000. And by the way, that's how bank interest works. You see, for bank interest, let me just do this one. Suppose I put money in the bank, 7% interest compounded annually. What that means is, at the end of each year, the bank gives me $7 for every $100 I've invested. So if I start with $100,000, at the end of the first year, the bank gives me $7,000. So now how much money do I have? I have my $100,000 plus the 7 the bank gave me, so I now have $107,000. By the way, if you want to do this problem in one step, each dollar is now worth $1.07, so multiply the $1.07 by 100,000. In other words, each dollar is worth $1.07, and you have $100,000, so it's 1.07 times 100,000. But the real neat thing is that starting the second year, this is your new amount. You're earning the interest not on the 100,000, but on the 107,000. You see, you got 1.07 return factor the first year. Now the second year, it's being multiplied by 1.07 again. You see, you don't just get 7,000 and 7,000. Your interest is earning you interest. If you multiply this thing out, you're going to have what? $114,490. You see, you gained $490, and this goes up very fast. In fact, we sometimes use this in reverse. This is where the algebra comes in. For example, let's suppose after 5 years, I want to have $100,000 to do something with. I can put the money away today. And let's say I can earn 7% interest compounded annually. That means whatever amount of money I put away now, I'll multiply it by 1.07 in value the first year, then 1.07 again the second year, etc. And the question is, how much money should I put away now to be able to have $100,000 5 years from now? Do you see where the algebra problem comes in here? See, now the variable is the amount I'm going to put away now. I'm multiplying by 1.07 5 times, so it's blank times 1.07 to the 5th power equals 100,000. I want the blank by itself. the blank is being multiplied by 1.07 to the fifth power. So to undo multiplying by 1.07 to the fifth power, I have to divide by 1.07 to the fifth power. By the way, if I want to do that longhand, I don't mean longhand, but just with the division key on the calculator, it just means what? Start with this number, divide by 1.07. Whatever answer you get, divide by 1.07 again. Whatever answer you get, you divide by 1.07 again. Do that 5 times altogether. And what you find is this would be the amount of money you'd have to put away today at 7% interest compounded annually in order to have $100,000 5 years from now. By the way, let me explain one more thing to you in terms of consumer protection. Sometimes you'll see a place that advertises, buy now, but no payments for 5 years. Sounds great, but in small print it will say, interest continues to accrue. And what that means is, if you bought something for $81,000 and you were paying interest at 7% compounded annually, and they weren't charging you anything but the interest, you didn't have to pay anything back, but they were charging you the interest, 5 years later, you don't owe $81,629.79, you owe $100,000. And that's why places are sometimes very, very lenient about having you not bother paying back as long as you pay back the interest. That's why a lot of your bank cards will say a minimum payment. They forget to tell you that your interest is going to be computed on the balance. So the bigger the balance, the more you're going to be paying them. But it looks good to only pay a small amount each month. By the way, I don't want you to think that exponentials are used only for money. Here's the situation with tossing coins. See, suppose you have a penny, a dime, and a quarter. How many different ways can the coins turn up heads and tails? Well, you see, the penny can be either heads or tails. No matter how the penny turns up, like if the penny is heads, the dime can also be either what? Heads or tails, right? No matter how the penny and the dime turn up, the quarter can be either what? Heads or tails. Every time you add one more coin, you're doubling the number of possibilities. See, with 2 coins, there are 4 possibilities. See them? Head, 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 tail, tail, head, tail, tail. With 3, it's head, 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 tail, tail, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. In other words, the chances of throwing 3 heads with 3 coins is what? Only one way out of 1, 2, 3, 4, 5, 6, 7, 8. Same logic applies to a football pool. Instead of heads and tails, you either win the bet or lose the bet. So on the first game, you can guess correctly, either winning or losing. No matter how you pick the first game, there are 2 choices for picking the second game. And no matter how you pick the first 2 games, there's still only what? 2 choices for picking the third game. So by the time you've picked 3 games, there are what? 8 possibilities. You have to win all 3 times to win. So therefore, your chances in winning are 1 out of 8. There's a lot more that we could do with this. The thing I would like to close with, though, is to show you how nice exponents are when you're dealing with powers of 10. You see, what's interesting is, let me just show you something else first. Suppose I'm looking at powers of 2. See how they go? 2, 4, 8, 16, 32. If I say to you, what's the 20th number on this list? There's no fast way of getting there. Count by 3s. Multiply by 3s. 3, 9, 27, 81. What would be the 20th number? Hard thing to do. The only easy numbers in the single digits are 0s and 1s. No matter how many 0s you multiply together, the answer is 0. No matter how many 1s you multiply together, the answer is 1. Well, the thing I wanted you to see is that 10 is a wonderful number from this point of view. You see, what happens when you have 1 factor of 10? The answer is 10. 2 factors of 10, see 10 to the second power means what? 10 times 10, which is 100. 10 to the third power is 10 times 10 times 10, which is 1,000. Do you notice what's happening over here? Notice that the answer is always a 1 followed by the number of zeros that the exponent is equal to. See, a 1 followed by 1 0, a 1 followed by 2 zeros, a 1 followed by 3 zeros. What would 10 to the 20th power be? It would be a 1 followed by 20 zeros. And look how compact that is. You see, look at how we can write certain numbers. What would 7.3 times 10 to the 8th power mean? Every time you multiply by 10, you move the decimal point 1 place to the right. Since you're multiplying by 10 8 times, what are you going to do? You're going to move the decimal point 8 places to the right. Well, there's only one digit to the right of the decimal point. To move it 8 places, you need 7 placeholders, so we tack on 7 zeros, and you see what happens over here? We get 730 million. This is a much more compact way of writing this, and notice that by having this being a number between 1 and 10, this number over here gives you a pretty good estimate of what the answer is going to be. See, 10 to the 8th power is a 1 followed by 8 zeros, which is 100,000. There's what, 9 digits there? That tells you that if you multiply this by any number that's less than 10, the answer will also have what? 9 digits before a decimal point. 3, 6, 9. See, these are all very powerful concepts, and I think it's about time to wrap up this session, because all I really wanted to do here is to show you the power of exponent notation and how it comes up in an algebra course. So basically, there's a couple of things that we can do here. We will be doing much more work with exponents as the course goes on. In fact, there'll be certain chapters in our course that will be really high-powered exponents. But for the most part, I just want you to get acclimated for now. If some of this stuff looked kind of hard for you, remember what we always said. Study over whatever portions of the lecture you want to study over. We're going to do some more work with exponents in our next lecture. But until our next lecture, just continue to study hard, have fun, and stay young.